everyone, and welcome back to the security of quantum key distribution. Last time we have studied classical information and classical entropies. So this time we want to talk about quantum entropies and variants thereof, like the conditional quantum entropy or the joint quantum entropy, very similar to what we did in the classical case. And even though the definitions and the formulas will look quite similar to their classical counterparts, we will discover some properties that only appear in the quantum world. And some of them are actually really surprising. Furthermore, we want to talk about the entropic uncertainty principle. That is a reformulation of the uncertainty principle by Heisenberg, which takes into account that we can have correlated quantum systems. And here, entropy is exactly the quantity we need for that. So, in the classical world, the uncertainty about a random experiment is quantified by the Shannon entropy of the random variable that models the experiment. In the quantum world, the uncertainty about a quantum system is quantified by the quantum entropy of the quantum state the system is in. How do we define the quantum entropy of a state? Well, it is quite similar to the classical definition of entropy. So suppose we have a quantum system A, which is in the state rho A. Then the entropy of the state is defined as minus the trace of the state rho A times the logarithm of the state rho A. So first, I want to shortly talk about the notation we use here. So in the definition, I've used the notation that I put the system A in the brackets and put the state rho into the subscript. We can also neglect the state rho completely if it is not important or clear from the context, but we could also even neglect the system and put the state in the brackets if we want to emphasize the dependence of the entropy on the state, for example. And throughout this talk, we will use these notations interchangeably. Okay, so how is this definition similar to the classical definition? Well, suppose we know the spectral decomposition of the state rho A. That means we know that rho A is of the form lambda j, the eigenvalue of rho A, times the pure state psi j, and we sum over all the possible indices j here. Then the entropy is a direct function of the eigenvalues lambda j. So the entropy of the state is then simply given by minus the sum over lambda j times the logarithm of lambda j, and summed up over all j. So if you remember that the eigenvalues of a state form a probability distribution because they are always greater or equal to 0 and they sum up to 1, then we can view this as the Shannon entropy of the random variable that is modeled by the probability distribution given by the eigenvalues of rho. And in this sense, it is basically the same as the quantum entropy. How do we interpret the quantum entropy? So suppose we have two parties, Alice and Bob, and Alice prepares quantum states. We call these quantum states psi x, and she prepares a state psi x with a probability p of x. When Bob is now wondering what Alice's state actually is, from his point of view, the state she prepares is rho A, where rho A is the density operator that we can construct from the ensemble that p of x and psi x form. And to quantize the uncertainty he has about Alice's state, we simply calculate the quantum entropy of the state. This is similar to the classical case where the uncertainty that Bob has about a random experiment that Alice performs is also simply computed by the entropy of the random variable that models the experiment. Okay, let's talk about some mathematical properties. First of all, the quantum entropy of a state is non-negative for all density operators. So if you remember that the quantum entropy is simply a function of the eigenvalues, and in this sense it is the same as the Shannon entropy, then this directly follows from the classical case. Okay, the next thing is a bit more interesting. It is the quantum entropy of a state vanishes if and only if the state is a pure state. So let's prove the statement. Suppose the quantum entropy vanishes. Then we know that lambda j times the logarithm of lambda j equals 0 for all j. And here again, lambda is an eigenvalue of rho. And to fulfill this equation, there are two possibilities. Lambda j could be 0 or it could be 1. At the same time, the sum over all lambda j's has to equal 1. This means that there is exactly one j star, I name it here, for which lambda j star equals 1. So in the spectral decomposition, the sum has only one term. And this is the same as saying that the state is pure. On the other hand, if rho is a pure state, we only have one term in the sum of the spectral decomposition. And when we then calculate the entropy of the state, we directly see that it is minus the logarithm of 1, and that equals 0. So we have proven that the quantum entropy vanishes if and only if the state is a pure state. The next property is that the value of the quantum entropy is upper bounded by the logarithm of the dimension of the system. This is similar to the classical case, where the entropy was upper bounded by the logarithm of the size of the alphabet, and so the quantum property can be proven analogously to the classical case. The last property I want to mention is that when we apply an isometry to the state, this does not change the entropy of the state. So applying an isometry means we have a matrix V that we apply from the right and from the left, and when we use the spectral decomposition of the state, then the isometry acts on the basis states psi j. And they simply map these states psi j to a different basis that we call psi j prime. So the only effect that this isometry has is that it transfers one orthonormal basis to another one. And so the eigenvalues of the state, they did not change. And since the entropy is only a function of the eigenvalues, the entropy also did not change. Okay, so after we have seen the definition of the quantum entropy and some mathematical properties, we want to talk about different variants of the entropy. Most of them are analogous to the classical entropies that we have seen, for example, the joint entropy, the conditional entropy, and also the mutual information. But one of them, the so-called coherent information, is something that we haven't seen in the classical case. And you will see why in the classical case this is not an interesting quantity. But in the quantum case, it is actually something that we are interested in. Okay, but we start with a joint quantum entropy. So suppose we have a bipartite quantum state that we call rho AB. Then the joint entropy of the state is defined as minus the trace of this bipartite state times the logarithm of the bipartite state. So it is completely analogous to the definition of the quantum entropy we have just seen, only that now we consider a bipartite state instead of the state of a single system. If you remember the classical joint entropy, then you might also remember the relation that the joint entropy of two random variables x and y is always greater or equal than the entropy of only one of the random variables. In the quantum world, the analogous inequalities are not always fulfilled. We will see an example. So consider a pure bipartite state. This has the Schmidt decomposition in terms of a basis EI for system A and a basis Fi for system B. And as we know from the Schmidt decomposition, the marginal states for system A are simply those density operators we form with the basis EI, and for system B, it's simply the state we form with the basis Fi. But the eigenvalues, lambda I prime, they're the same in both cases. Okay, we know that the joint entropy of the state is 0. We have seen that in the state of the entropy of a single system, if the state was pure, then the entropy is 0. And because for the joint entropy is defined completely analogous, only that the state is now a bipartite state, with the same reasoning, we can prove that for pure bipartite state, the joint quantum entropy is also 0. Okay, so the joint entropy is 0. But what about the margin entropies, so h of A and h of B? Well, since the marginal states are not pure states, these entropies do not necessarily have to be 0. They can, of course, in some special cases, but they don't have to be in general. And also very interesting, they are actually the same, because they only depend on the eigenvalues, and the eigenvalues of the marginal states, they're the same. This is very different from the classical case. So not only are these inequalities not fulfilled in general, that we have stated above, but also the entropies of the marginal states, they are the same. Let's see an actual example of that. So you probably remember the bipartite entangled state phi+. We have seen it a lot in the last video. It is simply the state 0, 0 plus 1, 1 divided by the square root of 2. The marginal states are the maximally mixed state for both systems. These are denoted pi A and pi B. We can now compute the entropies that correspond to these systems. So, since the state of the joint system is a pure state, we know that the joint entropy is pure, is 0, but because the marginal states are not pure states, they are actually maximally mixed states. So if we calculate the entropies of those states, then we know that it's the logarithm of 2, and that equals 1. So here is an example where this inequality that held in the classical case is really not fulfilled. Okay, let's come to the conditional quantum entropy. So the definition of the conditional quantum entropy is completely analogous to the classical conditional entropy. Namely, if we have a bipartite quantum state rho AB, then the conditional entropy of A conditioned on B is defined as the joint entropy of A and B minus the entropy on B. And here I didn't mention this before, but it actually also holds for the joint quantum entropy. If I write something as the entropy of system B and indicate it with the state rho, which actually is a state on A and B, then I mean that we calculate the entropy with the marginal state that we can get from rho by tracing out system A. This is what this notation means. So whenever I have indicated like a bipartite state here, but the entropy is only taken over a single system, then it means we use the marginal state that we can get from the bipartite state. Okay, so let's talk about the conditional quantum entropy in a specific example, namely again the state phi+ that we have seen so often. Remember, we have just calculated the joint entropy and the marginal entropies in the previous example, where we have seen that the joint entropy is 0 and the marginal entropies are 1. If we now use the definition of the conditional quantum entropy, which is the joint entropy minus the marginal entropy, then the conditional entropy is minus 1. Okay, wow, what do we make of this result? What does it mean that the conditional entropy is minus 1? We have never seen this in the classical case. In the classical case, entropies cannot be negative, but in the quantum case, they actually can. So one way to interpret this result is that a conditional quantum entropy simply means that we we know more about the joint system than we know about its parts. And this is actually true if we have an entangled state as above. We know exactly in what state the joint system is, because we know it's in this pure state phi plus, but we do not know much about the local states. They are described by maximally mixed states. So this means that a negative conditional entropy tells us that we know a lot about the joint system, but we know less about the individual parts of the system. This is something that can only happen in the quantum case. In the classical case, if we know exactly the state or the random variable of the joint system, then we also know exactly the random variable of the individual systems. So here, this is some fact that clearly distinguishes the quantum world from the classical world. And we can actually prove a theorem which tells us that this doesn't only happen for the state phi plus, but actually for all pure bipartite entangled states, the conditional entropy is 0. And the other way around, whenever we get a negative conditional entropy for a pure bipartite state, we know it's entangled. Let's prove this theorem. So first of all, note that if we have a pure state, the joint entropy will always be 0. This means that the statement above simply reduces to that a pure bipartite quantum state is entangled if and only if the marginal entropy of system B is greater than 1. Okay, so let us prove this version of the theorem. First, suppose that the state is entangled. That means its Schmidt rank is greater than 1. That also means that for Bob's marginal state, rho B, that we can get directly from the Schmidt decomposition, we have at least 2 terms. But that also means that the state is not pure, and therefore the entropy of the state cannot be 0, because before we have proven that the entropy of a state is 0 if and only if the state is pure. Okay, this is one direction. The other direction is that we actually have a marginal entropy per Bob system that is greater than 0. Then again, we consider the spectral decomposition that we get from the Schmidt decomposition, but this time we do not know anything about the Schmidt rank, because so far we do not know whether the state is entangled or not. But consider the case that the state is not entangled, so the Schmidt rank is equal to 1. This means that we also have only one eigenvalue that we call lambda squared, which is equal to 1, which also means that the entropy of the state is equal to 0. So this is a contradiction, because in the beginning we said the entropy is greater than 0, and now we get that it is 0. So the Schmidt rank has to be greater than 1, and therefore the state has to be entangled. The fact that the conditional quantum entropy can be negative is so amazing that people have actually defined an own quantity for the negative of the conditional quantum entropy. This quantity is called the quantum coherent information, and it is simply defined for a bipartite quantum state as the entropy on system B minus the entropy of the joint system. And as you probably have seen, this is simply the negative of the quantum conditional entropy. But people have soon discovered that this is a quantity in its own right. It is very useful in several applications, so they keep it, even though they could express it simply via the conditional quantum information. And this quantity does not appear in the classical case, because in the classical case, why would you be interested in the negative of the conditional information? This does not make much sense. A quantity that we have actually seen in the classical case is the quantum mutual information. So this is again defined analogously to the classical case as the entropy of system A plus the entropy of system B minus the joint entropy of system A and B. Okay, so now we have seen lots of variants of the quantum entropies, some very surprising facts of quantum entropies. We now want to get to the entropic uncertainty principle. So you have probably seen in your quantum mechanics course Heisenberg's uncertainty principle, where he talked about the uncertainty between the measurement of position and the measurement of momentum. Well, when we consider information theoretic tasks, this notion of uncertainty is very unsatisfactory. So one reason is that the Heisenberg's uncertainty principle was formulated in terms of the standard deviation of an observable. But for information theoretic tasks, there's no really nice operational interpretation of this quantity. On the other hand, for entropies, we have lots of nice operational interpretations, which we have seen throughout the videos. So it would be nice to have some sort of uncertainty principle that is formulated in terms of entropies. And another reason that Heisenberg's uncertainty principle is not very suitable for our information theoretical tasks is that it sometimes does not seem to take into account that quantum systems can actually be correlated and entangled. And I will show you an example where Heisenberg's uncertainty relation is quite misleading. So consider the entangled state phi plus that we have now seen a lot of times. And remember that for once it can be expressed in the computational basis, as we usually do, but equivalently, way to write it down is to use the Hadamard basis with plus and minus, because it's also a basis for qubit states. Okay, so now suppose that Alice measures her part of the system with the Z operator. For the Z operator, the plus and minus states are eigenstates. So from the first expression we gave for the phi plus state, we can see that Bob can actually predict her outcome with certainty. So Alice measures her state, she tells Bob which measurement she did, then he can measure his state in the respective basis, and from the outcome he can directly tell what Alice's outcome was. Because if he measures a 0, he knows that Alice must have had the outcome plus 1, because plus 1 is the eigenvalue that corresponds to the state 0 for the Z operator. If Bob finds his state to be in the state 1, he knows Alice has gotten a minus 1, which is the eigenvalue corresponding to the 1 state. So after he knows which measurement Alice did, he knows exactly, just by looking at his part of the system, what outcome she got. And similar, if Alice measures in the X operator, which is a measurement in the plus-minus basis, with the same kind of argument, Bob also can predict her outcome with certainty once he knows what kind of measurement Alice did, because Bob has to know in which basis Alice measured, so he can use the right basis to measure his qubit. Okay, so apparently Bob can predict Alice's outcomes if she does an X or a Z measurement both times with certainty. But the problem is, Heisenberg's uncertainty relation tells us that Z and X are incompatible measurements. Something seems to be not right here. And the problem is that Heisenberg's uncertainty principle does not take into account that the two systems are entangled. So what we would like to have is an uncertainty principle that is formulated in terms of entropies, because they seem to be the right measure of uncertainty in the kind of scenarios that we look at here, and which also takes into account that systems can be correlated or entangled. Okay, so let's have a look at how we can define such an uncertainty principle. As always, we start with our two parties, Alice and Bob. Suppose Bob prepares a bipartite quantum state rho AB. He keeps one part of the system, B, and he sends part A of the system over to Alice. Similar to what we described before, Alice can then do a measurement, and she can choose between two measurements, either the Z measurement or the X measurement. Apparently, she gets some outcome theta out of that, and then she tells Bob which measurement she did, so if she did the Z or the X measurement. Bob now wants to know what Alice's outcome was. So in the previous scenario, we saw that he can predict the outcome with certainty. But of course, this doesn't have to be the case for every bipartite quantum state that Bob can prepare. So how do we quantify the uncertainty that Bob has about Alice's outcome? Let us retrace the steps I just talked about mathematically and a bit more general. So suppose Alice can choose between two POVMs that she wants to measure. So she can either do the POVM described by M or the POVM described by N. Suppose she chooses to measure the POVM M. The state after measuring is then given by the following state I call sigma xb, where we have the outcome X that Alice got encoded into quantum states, and the tensor product with the trace over Alice's system of the state rho AB, where we have applied the measurement on Alice's part and the identity on Bob's part. So the state we have here on the right is actually the state that Bob holds after Alice has done her measurement, and the state on the left describes the measurement outcome that Alice got. And we sum over all the POVM elements, so over all the outcomes that Alice can get. Bob's uncertainty about Alice's outcome is then described by the conditional quantum entropy of X, which is now a classical random variable, conditioned on Bob's quantum system. On the other hand, if Alice measures the other POVM, N, then we have a similar state, only that now the outcomes are called Z, and the measurement is N instead of M. And here, analogously, Bob's uncertainty can be quantified by the conditional entropy of the random variable Z conditioned on Bob's system, and evaluated over the state tau now. Bob's total uncertainty, because we have to take into account the uncertainty about both measurements, is then simply the sum over these two conditional entropies. Okay, so in the same fashion as for the Heisenberg uncertainty principle, we want to have a lower bound on this uncertainty. And the lower bound that we can get on this uncertainty is the logarithm of 1 over c plus the conditional entropy of A conditioned on B. And C here describes the incompatibility of the two POVMs that Alice can measure. So this is a quantity which only depends on the two POVMs, but not on the state the system is in. And it is given by the maximum over all the possible POVM elements, which are here the index by X and Z, of the infinity norm of the operator the square root of the M POVM element times the square root of the N POVM element. And the infinity norm of the operator is, in the finite dimensional case, simply the largest eigenvalue of the operator. So this is the entropic uncertainty principle for the scenario we described here. And one thing you should notice is that we have a sum of two terms, where the first term only depends on the incompatibility of the two measurements, and the second term only depends on the state the system is in. And as we have seen before, since the conditional entropy can become negative, the lower bound of the uncertainty can actually become lower than the term that describes the incompatibility of the two measurements. So if you choose the right state for your measurement, you can actually decrease the uncertainty to 0. Not in all cases, but sometimes. So we won't prove this lower bound here, but you can find it in a paper by Mario Berta and others, which was published in Nature Physics, and which is called the uncertainty principle in the presence of quantum memory. So there they gave a proof for this uncertainty relation. We will now have a look at an example for this uncertainty relation. And you might have guessed it. Again, we consider the stage phi plus that we have seen now quite a few times. And the POVMs for the Z measurement. So the POVM for the Z measurement is given by the POVM elements constructed with the 0 state and the 1 state. And the POVM for the X measurement is given by the corresponding POVM elements constructed from the plus and the minus state. And you can calculate this parameter C to be 1/2. And we have calculated before the conditional entropy of the state, which is -1. If we now evaluate the entropic uncertainty lower bound, then we have to calculate the logarithm of 2, which is 1, minus the conditional entropy, which is plus the conditional entropy, which is -1, and then we apparently get 0. This is very consistent with the observation that we made before, that in the scenario we described in the beginning, Bob can actually predict the outcome with certainty. Since the lower bound on the uncertainty is 0, this is definitely possible and correctly represented by the entropic uncertainty principle, in contrast to Heisenberg's uncertainty principle. So this seems to be a very useful quantity for the information theoretical tasks that we want to do. So we come to the end of the video. We have seen quantum entropies, we have seen variants of quantum entropies, and we've seen some very surprising facts at first sight. We also have studied the entropic uncertainty principle. And now we are actually done with the mathematical tools that we need and with all the entropy stuff. So next time we can go to QKD protocols. So we will talk about prepare and measure protocols and what's the difference between them and entanglement-based protocols. And we will go through the various steps of a QKD protocol. So thank you for watching, have a nice week, and I hope to see you next time.